performance improvement. And here the BS 1192 approach to bring together project information and asset information prescribes a common data environment as the approach to do that. And a common data environment wouldn't reincarnate the native information, but rather files, models, and components would be federated and indexed together. We use for that a technology that recognizes the intelligence and semantics of those components and how they relate to each other so that we can track the relationships and in particular the changes as they occur during projects and operations, and would know from those interrelationships what is affected and depends upon such changes. So that's our approach to a common data environment, to incarnate, federate, index, make available digital engineering models for smart infrastructure. Now Ross Denton later in the morning is going to talk about Crossrail's approach to relating the virtual and the physical, so I won't say much about that as it relates to asset tag mobility in ways such as Professor Starr referred to that didn't exist. Computing was on desktops and on-premise servers, and now is in cloud services, on mobile devices, private clouds, and you can't tell where one starts and the other leaves off. So a common data environment today involves the devices in the field, especially, and new ones all the time. So incarnating that common data environment in the Azure cloud is what we had recently helped Crossrail to do. So we've transitioned to a managed service where we at Bentley Systems provide not only the software, but using the Microsoft Azure cloud, the underlying infrastructure under a service level agreement, which will help provide that common data environment all the way into operations of Crossrail. And speaking of operations, we look forward to speakers here from New York's Metropolitan Transit Authority. The MTA has also now selected our asset-wise environment to help with their decision support and reliability environment for their network. But back to BS 1192 and projects to assets, it's all about information delivery, and there's a particular innovation that has helped in regard to that, where the common data environment is now connected through apps and through containers for information delivery and work packages that we call iModels. iModels are important factors in the success of many of the 2015 projects. And what iModels are used to deliver information for a particular purpose, so they know the provenance for which they are created and can be secure and limited to that purpose. They always include the schema which describes the work package inside the iModel. Now that can be in the form of a comprehensive data standard, but if it's not, you can still interpret what's in an iModel work package by reference to the rows and columns and table structure of that self-describing schema. And I think it's a terrific way to improve engineering collaboration beyond the limits of today's comprehensive standards. And iModels include engineering precision. But something over the life of iModels that we've added is mobile containers. And a case in point of that is that we and Topcon this month have announced collaboration by way of iModels between our ProjectWise collaboration environment and their corresponding environment for civil heavy construction on site, so that workflows can be in both directions to provide directly the machine controlled grading, for instance, and bring back to the design environment, the as-built civil workflows. Back and forth to the field, which is the data management missing link, if you like, today. But consider when we talk about data management and asset information in the field, the case of Western Power in the UK, the largest electric distribution footprint, and there they have implemented in the field, every technician has the whole network in the field so that they can respond to any emergency. Think of the number of changes in the network and how hard it would be to synchronize those iPads if every time the whole network model for the whole of Western Power would need to be provided. So we developed a technology we call change sets, so that iModels, which know the provenance for which the information work package was first provided, will therefore know only to provide those changes to it. And think of how much more practical that is for an information management environment during asset operations for just those changes. So in that common data environment, now talking about the asset performance side, and to realize the potential of these digital engineering models, all the way to asset performance modeling, my example here is South Australia Water, that they built a desalination plant that was a winner in terms of design modeling in 2012. In 2015, that's now come online, and our winner in innovation and asset performance was South Australia Water, whose presentation, I'm going to paraphrase here now, but it's available on our website and well worth the 20 minutes to understand how they went from digital engineering models to a decision support system. They are in the driest state, in the driest continent in the world, and there's Rowan who did the presentation. He's in charge of their distribution optimization, and when they added the desalination plant, on the one hand it's very expensive to run, it uses pure energy to create water, but also their network prior to that had all the water sources up in the hills, and gravity could feed their uses. But obviously a desalination plant is at sea level. And now they had to make their distribution network much more flexible. But with that came degrees of freedom in how to operate the network so that they could go from standard operation to the pumping operation. And really, in Australia, it turns out that 40% of electricity generated in South Australia is from wind already, on some days 100%. And by the way, electric rates therefore are very volatile and can go negative, but they vary consistently throughout the day. So South Australia Water, whose network you could think of as a pump storage facility, has the ability to take advantage of their network model to optimize for that. But this is, as Rowan describes, the challenge they faced to begin with. How could they possibly meet that challenge, the one that Professor Starr described, of having too much data? So the answer was that we have good software called Amulet to connect up to operational technology inputs, to connect up to the hydraulics and hydrology model done with software like ours for the design and operation of the actual network, and to start by using Amulet to interpret the weather forecasts on a real-time basis to understand what the demand would be. So they started with a demand forecasting tool running in right time, if you like, not quite real time, but every half an hour. How different does it look? How much will our water demand change? And then knowing exactly what the condition is of the network and what the hydraulic and hydrology model provides, and then looking at the cost of power and creating dashboards in Amulet here to be able to look at what the operation of the network is at any given time and what it has been and what it's forecast to be, and then include their water quality sampling and so forth in these dashboards, and then ultimately to save money in And they actually go out now and purchase their energy on the spot market with this wired up example of asset information and data management for smart infrastructure to save power to start with and then to improve each year, as he described, in their network operating costs. So that's the best example we've seen so far. There's Rowan in his control room now taking full advantage of having come that far. And it's such a success that Gartner actually wrote up this example, and you may obtain the lessons learned. They phased in these multiple dashboard approaches for a successful operational intelligence system. So my next example here in the UK is the 7th largest infrastructure asset owner in the world, the Highways Agency, now Highways England, and their integrated asset management information system includes the spatial context of the roadway network and maintenance requirements for it. And here, the asset-wise environment is being used to cope with, if you like, a different kind of clash. These are all the maintenance events scheduled and planned on the main roads here in England, and to make sure that there are the minimum of such interruptions, and to look at clashes between scheduled maintenance and how those are resolved is a good use of this common data environment here in England. Now, we might wish to go further than that and have our project-wise CapEx environment tied in. So this is the Connecticut Department of Transportation and their asset-wise environment. They can go and see all of the capital projects that are occurring on their network, and with the appropriate security, go into the project-wise environment. So this could be, by the way, the asset-wise environment is open to any citizen, and then the Connecticut DOT people can go in and look at the status of any capital project. All of the drawings and models are available. And now this has been extended so that they use ProjectWise as well to make available the bridge inspections. So for instance, they might search here on a roadway, find it has bridges, for one reason or another want to know what's the latest inspection report for the bridges. They use our AssetWise InspecTech software for bridge inspection. But to bring in a common data environment, the CapEx and the OpEx side seamlessly like this is what we would like to help make possible in general. So if you go now into the records related to the bridge inspections, they're all federated and indexed together, as you see here. Now, what about connecting in the other direction to the reliability environment? So here is an AssetWise environment with an alarm showing. It's a substation, and here, to the extent, in this case, that there would be digital engineering models available. Suppose this is the plant, and the alarm would take you to exactly the component that's failing. That component would have available its degradation history and failure mode to help you make the decision about replacing it. And that could be in this greenfield site, if you like. Here's a transformer where our reliability software is using real-time monitoring to come up with a health index, if you like, about that transformer. But this takes me to my suggestion for what's possible now with a cloud service, to have the intelligent components linked together all the way from design through operations. And we did do this through a piece of software we call Component Center, where a catalog service is available. We're here in the Bentley substation application, and we could choose available transformers we had their specifications available. This is all not in the design environment, but in the Azure cloud environment. All of the documents, including information about their failure modes, and those we'll accumulate and keep up to date. And as we would learn more in our design teams about those components, these would be the ones prescribed by the owners that they want used in their projects, and information would be accumulated to be reviewed by others, and we would have all of the information, including across the life cycle. For instance, to start with, the fabrication strategies for these components so that they could be off-site manufactured, and then in commissioning their data sheets and maintenance plans. And then during maintenance, we would accumulate the failure modes information across our fleet and continue to make that common data environment related to those components, the systems engineering approach, if you like, smarter and smarter and smarter in all of these terms. And we could all reference that improved digital engineering model information through the Azure cloud. So you might say, that sounds really good if we could start with a greenfield and do things that way. What about the real case where we don't seem to have the engineering technology, the digital engineering models available? They were created by someone sometime, but we don't know where they are. We can't take advantage of them. Well, we do have an advantage now in a new innovation to talk about. So it turns out that in everything we do in our software for design modeling and analytical modeling, construction modeling, and asset performance modeling, we have a big advantage. All of the virtuality, if you like, all of the virtual data has a 3D geo-coordination that's in common with the reality in which we construct and maintain these assets. And so a strategy called reality modeling to bring this together, and you might say that can start with laser scanning, but there's a new approach to using digital photography alone. So we did a project in Philadelphia. I'm going to describe a bit more of it. This is using software to create from standard available, commercially available imagery, but processing it to aerotriangulate. As you see, you could do this for any of your assets today from what's already available on the web from aerial photography that exists. But we wanted to engineer Philadelphia for the Pope's visit last year, and that required greater accuracy. So digital photography was used at street level, and in this case from a helicopter, but this can be from UAVs and drones, to take over the course of the day, and this could be repeated as often as you like for continuous surveying. I'll just go back to show the way the software works. So here, this is where the Pope did a mass in Philadelphia. So here are photographs taken that are dragged and dropped into the software. This is the extent of the interface. It knows we have these photographs. They're taken with an ordinary camera, could be a cell phone even. And the software asks you to confirm. This is where it has worked out the photographs were taken from, their angles and so forth. And if you press the button, it's going to go on to solve for the reality mesh, the 3D model that's created from those photographs. And it may process for a few hours, or you can do it faster in a cloud service, and produces now not a point cloud, which is done and large, but an elegant mesh that is the basis, as we'll see, for engineering. So this then is the resulting reality model, reality mesh of Philadelphia, and it was used to bring, it's engineering ready. That mesh was used by our folks to engineer the temporary structures for the Pope's visit here in Philadelphia. And you can get any level, virtually any level of accuracy with more photos and more overlap. It's not even very much limited by the resolution of the cameras. So let's go back to our brownfield reality of our infrastructure. So this is a substation in France. So in a few minutes from a UAV, a drone, 286 images were taken, And they were supplemented by walking around on the ground and taking 180 shots from a camera on the ground. And then a GPS control points were visible and included there. And it was decided to go a little bit further, in particular at the nameplates of the equipment. So that became a reality mesh that could be routinely surveyed and compared and differenced. By the way, a drone is not limited to photography. This is thermography that could show what's hot in that substation. And now, for smart infrastructure, our engineer's job, he doesn't need to go schlep out to the site and spend his time looking. He would use the result of the reality survey. And here, for instance, you can look at the nameplate on this equipment, relate that now to the maintenance and reliability records for that particular tag, look at the health index maintained in our Amulet software, processing the big data from operational technologies, and perhaps decide to replace that transformer. Now, here's the reality mesh captured by the drone. It goes directly into MicroStation, the Bentley substation application, where from the catalog we'll decide what transformer is to replace it. And all of that intelligence from the component service are now linked, if you like, in this mixed reality environment. We've just improved the substation. While we're at it, let's harden it. It's outside Paris with some lights and fences and so forth, but all in that same environment where we started with a brownfield, reality modeled it, have always an up-to-date mesh for continuous survey and inspection, and where the intelligence about what we've added to it, our digital engineering models, are there as well. And during the construction of it, if we would consecutively fly with the drone, as in this case, we can look at the difference from one flight to the other in construction progressing and statusing, and then ultimately compare that to the design model for the quality of the construction as it proceeds. Back in Philadelphia...
Please, Greg.
Pardon me?
5 minutes, please.
Right, okay. So we can use our new Open Roads Concept Station to improve infrastructure here, starting with actually working in the reality mesh to conceptualize a new bridge in Philadelphia and what its cost would be. So we've found a way through this reality modeling approach to get to asset performance modeling even in a brownfield. So I just want to conclude with some rail examples back to last year. So this is in Rio for the Olympics. And they're already using context capture. That's the software I talked about for their metro line in Rio. In this example, this is a derailment that occurred. A drone flew it and created a video which is on YouTube. We processed the YouTube video. The video amounts to the overlapping images, which you could use here to find what went wrong in terms of, and then inspect the remainder of the railway for such other risks. Now, this is the view you'd like to have from the driver's cab of signals and so forth for safety. But suppose, you might say you could generate that with a video on the train. This instead now is navigating, this isn't the helicopter flying, this is navigating a reality mesh, which you could then use to create the view from the train driver, but the advantage here is it's ready for engineering. It's an actual mesh. And the way that's done now here in the UK, you start with point clouds, as in this case, and Professor, I have 2 more examples only. And now bring together the digital engineering models of that signaling environment. And then the engineer in this common data environment can use the video, as you'll see, to actually navigate where he's working and doing the engineering. And that can include when we're far enough out, I guess, where we need to electrify this track, use all of these modes of data, as you were saying, Professor, where it's an abundance of data in all these types. If we're electrifying that, we're now looking at the virtual proposed electrification design moving along the video in MicroStation where we would edit and improve that design. So the LADS project for Network Rail uses our Optran software on iPads for the field superintendents to make better decisions about maintenance, which has saved a lot of money already, and we want to build on that for a more reliable railway in the UK. How would we build on that? So this is the Optran environment now, and suppose the train driver has reported rough track in this particular linear area. We see now the bridges that are there, and for each bridge we can see what the survey for all the metadata of the bridge, but we can look to see for a particular bridge what has the result of the maintenance activity in terms of quality of ride been. This one consecutively over time has been consistently good, so this can't be the one where the problem is. Move along the linear railway as the superintendent would do. Here's a bridge that has degraded over time, and what you would want now and are able to do you see, is to be able to say, at a point in time in history, there was a new design. Let's look at the new design. We're in the MicroStation environment. Let's bring up the reference of the maintenance information, the design information, and then we're going to see on the timeline that there was a point cloud survey done at a point in time. And that can be brought in and federated together into the design environment for a better maintenance decision. And this is all converging, if you like, for the OpEx and CapEx side. We have a symposium in our Rail Academy in September. Many of your organizations are already planning to be there, but we will surely want to be represented. And I just want to conclude with a testimonial for the work done when this gets put together by London Underground for a project which used the point clouds to occupy the tunnel only at night. And what did someone we know say about that? Oh, we have to hear Boris here now. Can we turn up the sound? I don't know if we can do that or not. He said, well done. The London Underground on this project. So in this convergence, I'm going to skip over one more example and just say that Singapore, when we talk about smart infrastructure, we think about Singapore. So Singapore is the winner in innovation in government in going, they have lots of space in Singapore, but it's above and below ground. So our common data environment for interoperability there is really useful. These are their slides from their presentation. You can see it on our website. But ultimately, here again, that's a digital engineering model that was created with our software some while ago and can help with smart infrastructure in Singapore. And in 2017, I hope you will join us in Singapore for our Year in Infrastructure Conference 2017. This year, we're again in London in November. See you then. Thank you very much.
Hi, my name's Paul Sholcock from Opera. I was interested to see on the virtual mesh, basically the speed at which you can generate the mesh models. Have you got further and developed how you can actually identify?
For instance, the components are designed and placed in Crossrail, for instance, are already geo-coordinated. The objective is to be able to show the classification of the assets in their relation to the mesh, so that each time the mesh is resurveyed, so you can difference conditions as construction or operation progresses. You don't have to repopulate the asset registry, it does itself. The geocoordination is the way to do that, the XYZ references. And some other clues we're working on together. So some people in the room are contributing to that. I hope to be able to show that in November.
And will that be bi-directional, so from the asset registration, bring
Yes, we get one from me, which is, what are you going to do about legacy PDFs?
Well, that's one of the tricks. I mean, the PDF, so first of all, there's even such a thing as 3D PDFs. I don't know if you know that. And we produce 3D PDFs. So PDFs aren't all done, but they're mostly pretty done. So some of the tricks you go through are from context, from names, from some people even do OCR to PDFs. Can you recognize something which does have a geocoordination? So we're pretty good at connecting together everything that would use the same title block reference and so forth to nominate a geocoordination, which you could then edit if it weren't correct. But so I believe the first killer application for the immersive environment you can create with the reality mesh to be an as-operated 3D environment for every infrastructure asset, the first killer application will be just being able to find the information you already have, which can now be spatially related to that mesh. And the mesh will be on people's HoloLens or in their glasses or whatever, but they'll just be able to see, oh, we have a model for that, we have a data sheet for that, we have a PDF or a schematic, whatever, just to know it's there. And therefore, we're going to work hard at finding the clues with which you could show in an immersive 3D environment what information you already have, even if it's not an intelligent information. It's still something you otherwise weren't even going to bother to look for because you knew you couldn't find it.
Fabulous. Thank you very much, Greg. Can I ask you to thank Greg in the usual way?